Here we show the plan view of a Michelson interferometer. The laser source is located on the far right. It passes into a microscope objective that focuses and diverges the beam. The focus spot of this objective is spatially filtered by passing it through a pinhole before it is collimated by a positive lens in the right center of this image. In the left center of the image, the collimated beam is then split in two directions by a beam splitter cube. The far left optic is a flat mirror and the bottom optic is a flat mirror that represent the two paths of the interferometer. The beams are then recombined on a screen at the top of the image where the red dot is shown to create an interference pattern. Here's a side view of a Michelson interferometer. The laser source passing through the microscope objective and into the pinhole before being collimated by the positive lens, split by the beam splitter cube in two directions, and the beams are recombined on the screen to form a fringe pattern. A useful technique to align this system before producing the interference pattern is to remove the microscope objective, and when the microscope objective and pinholes are removed, a pencil laser beam passes through the whole system, and it is very obvious that there are two dots now on the screen, and when those two dots can be made to overlap, interference can be produced. So in the upper right we see the beam due to the path of the mirror at the front of the image, which is the mirror mount that I'm currently adjusting, and at the lower left dot is representative of the interference path created by the leftmost mirror in the interferometer. So to do a preliminary alignment, we want to make these beams overlap. We won't see fringes unless we do a very good job at this stage of overlapping them. But when we put the microscope objective back into the system, we can expand the beam and make the fringes more easily visible. Here we observe the fringe pattern of the interferometer. There are no fringes yet because the two paths are not aligned. However, by tilting one of the mirrors, I can create horizontal tilt fringes. There we have about 10 tilt fringes. That was achieved by just tilting one of the mirrors in elevation, and I can actually null the fringes by adjusting both the elevation and azimuth axis, the tip and the tilt axis of one of the mirrors. And you'll note that if I add tilt fringes deliberately with one mirror, I can go to the other mirror and take them out, because both paths of this interferometer contain flat wavefronts. Only tilt fringes can be induced through this interferometer. So we'll zoom back in on the fringes themselves, and we'll note that tilt fringes induced by one arm can be removed by the other arm of the interferometer until we have a single nulled fringe, as you see here. Also to note is that a negative lens has been placed after the beams were recombined, and that negative lens helps to see the fringe pattern more clearly. It should not be used for evaluation because any aberrations in any of the optics along the path will influence the quality of the fringes measured.